Following the same strategy, we can also make binary division on paper pencil. I'm not going in detail onto that. Just one point to note there, your quotient digit, there is no digit now, it is a quotient bit, can be either 0 or 1. So your multiplication value at the each partial computation is either your divisor or 0, right? So that's the one notation you need to make. Now think like, now here let me explain this what we are doing here, and also look at the iteration number for 8-bit values. Okay, 8-bit values iteration number, that's also important to understand. We need to use like 16-bit, both of them. Okay, in the one register we call remainder register, and other register we call divisor register. Remainder register is loaded on the lower half with the dividend bit pattern, and divisor register on the upper half, like 16, like upper 8 bit in this case, we load the divisor bit pattern. So that means you can well imagine for your 32-bit binary division, you need to have some 64-bit register. Okay, so lower half of the remainder register will be loaded with your dividend bit pattern, and upper half of the divisor register will be loaded with the divisor bit pattern, and there will be a quotient register which is 8-bit, or for 32-bit machine it will be 32-bit quotient register. And we'll see we need a shift capability also for all of these registers, shift capability. Okay, so it becomes a left shift, one become right shift. So in general we'll see what operation needs to be done there. Now imagine I have drawn this dotted line at the boundary of the 8-bit, like middle of that, right? And lower half is your dividend, upper half is a divisor. So what essentially you can make an analogy that on the paper pencil you are writing the dividend, and also at that left hand side like line, perpendicular line of before that you are writing your divisor. And what we'll be trying to do, we'll be trying to move the divisor into the right direction and place it under the dividend such that the subtraction result become a positive. Okay, otherwise we'll keep on doing that, putting quotient bit as 0. Okay, but if subtraction is possible, that means my quotient bit at that stage becomes 1. So let's see that. So we start with iteration number 1 and we subtract. So first few iteration it will always be a negative remainder. Okay, so we had a positive remainder to start with because it is loaded with the dividend bit pattern. Then we subtract with the divisor bit pattern, which is of course much bigger than now value wise from the remainder register. So it becomes your some negative remainder. So what we'll do for the negative remainder, left shift quotient by 1 bit and insert 0 at the LSB. So it is practically can be done with your left shifting 1 bit and or with a 0 at the LSB position. So that's what being done. Then if it is a negative also, we need to roll back the remainder. This is very important point you need to remember and understand. This rollback, will mention this same thing later in a separate discussion. So we need to roll back the remainder. So roll it back. So that means what? On top of this addition result, if I add back the divisor bit pattern, I get back. Then we right shift the divisor bit. Okay. So this is, remember, like we right shift the divisor bit and that brings us into iteration number 2. Till this point, this was iteration number 1. We finalize the quotient bit and then one shift, that is the last operation of iteration 1, and we go to the iteration 2. We repeat the same process. We subtract divisor from the remainder, test if it is a negative, insert 0 on the quotient left hand side, then roll back, then we shift the divisor bit pattern, and that brings us into the iteration 3. We follow the same thing. Okay, so subtraction, test, quotient finalization, rollback, shift. Subtraction, still negative remainder, bit insertion on the quotient, rollback, shift. Iteration 5, I think we are still more than the dividend bit pattern. Negative, 0, come back, shift, then do a subtraction, negative remainder, insert 0, roll back, shift. Now see, at the iteration 7, now we have a bit pattern in the divisor register which is less than your dividend. At this point, you can well imagine our subtraction operation will give a positive remainder. So if it is a positive remainder, then we insert a 1. We shift the quotient bit 1 position and or with 1, which insert a 1 into the LSB position of the quotient. Okay, and finalize the quotient at that point. And there is no rollback this time because it's a positive remainder. We keep it like that way and shift. So iteration 8, we do the same thing. This is still positive remainder, so we insert a 1, shift, then subtract, still a positive remainder, shift 1, and at this point we are done. Now see, for the iteration number, we need one more than number of bit in this process. So this is important. Okay, so that means for 32-bit division, you need to have 33 iteration. All right.